Section 7.5, Part 3. The other major concept in this section is the idea of independent events. In general, two events A and B are independent if the outcome of one does not affect or impact the outcome of the other. Think of rolling a pair of dice. What you get on the first die does not affect what you roll on the second die. Think about tossing coins successively. When I toss the first coin, doesn't impact what I get when I toss the second coin, doesn't impact what I get when I toss the third coin. So we have a test for independence. It comes in pretty handy. So our test for independence simply says that if you have two events, they're independent if the probability of their intersection is equal to the product of their probabilities. So if I multiply them together and I get the same thing that I would get if I found their intersection, they're independent. So let's try an example. So this is example, I think we're up to 7 for the section. So example 7. Consider the experiment of tossing a fair coin twice and observing the outcomes. So we're going to let E be the event of heads on the first toss. So E is heads on the first toss. So if we were to list those out, that would be a head, tail, and a head, head. So when I toss a coin and getting a head on the first toss is a head, the second would need to be a tail or a head. We're going to come in and let F be the event that we get tails on the second toss. So tails on the second toss, so that would be a head tail or a tail tail. Okay, what we want to do is show that these are independent events. So show that what I toss on the first one doesn't impact what I toss on the second one. So we found them individually. So here's the first event, here's our second event. We also need their intersection. So E intersect F. Well, we can see that there is an overlap. It's just HT. So one of them. Now we'll look at the probabilities. So the probability of event E, we know that there were 2 of them out of 4. And again, the 4 should make sense too, because if we toss a coin twice, there are 2 choices on the first one, 2 on the second one, so the sample space is 4. Okay, we know the probability of F is also 2 out of 4. And the probability of the intersection was 1 out of 4. For them to be independent, this one multiplied by this one has to equal that one. Let's reduce this. This is a half. This is a half. So what we're saying is 1/2 times 1/2 is equal to the intersection of 1/4. And this is true. 1/4 equals 1/4. So we've just shown that these 2 events are, yes, indeed, independent. How does that help me? Well, it helps me a lot. If I know things are independent, then I automatically know that intersection. Example 8, we have if A and B are independent. So they're telling me that those 2 events are independent. They're also telling me that the probability of A is equal to 0.4. The probability of B is equal to 0.6. Okay, what they want me to find, first of all, is the probability of their intersection. Well, they just told me they're independent, so therefore the intersection is the product of their probability. So 0.4 times 0.6, which is going to give us 0.24. That's because they're independent. So part B says, let's find the probability of their union. So we're going to go way back a couple of sections. So the union is equal to the probability of A plus the probability of B minus any overlap. Well, we now know that there's an overlap. So for us, A is 0.4, B is 0.6 minus the 0.24 that we found in their overlap. And that gives us 0.76. We can go a step further and deal with the conditional statements. The probability of A given B. Okay, I don't have a tree or anything else to work off, so I have to use the formula. So according to the formula, this is the intersection divided by what you know has already happened. So the intersection we found to be 0.24. B has already happened, so we'll pick up B, which is 0.6, which comes out to be 0.4. And what about D? D is asking for some complements. The probability of A complement union with B complement. Okay, I think the best way to get a handle on this, especially because you're looking for the union, is to draw a quick Venn diagram of what's going on. We didn't need to, but it definitely helps. So here's A, here's B. We know the intersection is 0.24. If we subtract our way out, 0.4 minus 0.24 is 0.16. 0.6 minus 0.24 is 0.36. And then if we add all of those together, that'd be 0.4, 0.76. That leaves me 0.24 left over. Okay, we're looking for A complement union to B complement. We'll do the check mark thing again. So A complement would be this region and this region. B complement would be this region and this region. Because we're looking for the union, we're looking for anything that has a check in it. So that would be the 0.16 in the first check, the 0.36 from our next check. Whoops, what was the decimal? And then finally the 0.24 that's staying out here. And if we add all those together, we should get 0.76. You'll notice I fell back on the Venn diagram to get a handle on it because it's just a nice clear way to illustrate what's going on to find those answers. Okay, let's do one more with independent events. This is example 9. Okay, so example 9 actually gives us a tree diagram. And so what we see are an A and a B. These are the first events. And their probabilities are each at 0.5. And then we see an E and an E complement. So E complement, E complement. So this is 0.4 and 0.6. And we have 0.3 and 0.7. So what this question is just asking us is, can we read information from this tree, use our formulas, understand what they're asking us? So part A is just asking for the probability of A. So I look at my tree. A is the first branching. All I have to do is pick off the first branching. So because it's part of the first branch, we can just pick the answer directly from the tree. Part B is asking for the probability of E given A. So we know that A has already happened. We need E to happen. Well, that's just the 0.4. I don't need a formula. I already know that this has happened. That's already narrowed down what branch I'm on. It's identified the branch that I'm on, and I know this is here. So what's E after that's already happened? Just the 0.4. Part C is asking for the probability of A intersect E. So when I do an intersection on a tree, I have to multiply across. So we're going to take 0.5 times 0.4. Notice that that fits what we already know. We can multiply across. That gives me 0.2. Part D on that problem is asking for the probability of E. Well, the difficulty here is that E occurs in more than one spot. E is right here, and E is right here. And I need to account for both of them. That's why I can't just pick one answer off. In order for E to happen, A had to have happened. Also, B had to have happened. So A, E, or B, E. So we're going to multiply across and then add those down. So we're going to take 0.5 times 0.4. Plus, and that's because there's the or statement. So this is an and, A and E happening, or B and E happening. So then we'll do 0.5 times 0.3. So when you figure that all out, it comes out to be 0.35. So very important, because E is the second branching of the second event to occur. In order for E to happen, we have to address both A or B happening. And then finally, the last question is asking us whether or not they're independent events. So in order for them to be independent, let's use our test for independence. So we're going to take the probability of A and multiply it by the probability of E and see if that's equal to the intersection. Okay, well, A we already know was 0.5. E we just found at 0.35. And then is that equal to the probability of the intersection, which was 0.2? So 0.5 times 0.35 is not 0.2. It's 0.175. And that does not equal 0.2. So they are not independent. So in other words, A is impacting E.